From the vast, sun-drenched expanse of tropical oceans, a monster is born. It begins as a whisper, a gentle disturbance in the atmosphere, but under the right conditions, it can grow into a colossal, swirling vortex of wind and rain, a cyclone. These powerful storms, known by different names around the world, like hurricanes or typhoons, are some of the most destructive forces in nature. But how do these behemoths of the atmosphere actually come into being? Today we're diving into the science of cyclone genesis, the dramatic story of how a calm patch of ocean can give birth to a raging, spinning giant. To create one of these massive storms, you can't just have one or two things go right. You need a specific, almost perfect set of atmospheric and oceanic conditions to align. Think of it as a recipe for a perfect storm, and it requires 6 key ingredients. First, and most importantly, you need warm ocean water. This is the fuel for the engine. The sea surface temperature must be at least 26.5 degrees Celsius, or about 80 degrees Fahrenheit, and that warmth needs to extend down to a depth of at least 50 meters. This huge reservoir of warm water provides the immense thermal energy needed to create and sustain the storm. Without it, a cyclone simply cannot form or survive. The second ingredient is atmospheric instability. This just means that the air is primed to rise. If you give a parcel of warm, moist air near the ocean's surface a little upward push, it won't just stop. It will continue to rise on its own, like a hot air balloon. This happens when the surface air is much warmer and more humid than the cooler, drier air high above it. This instability allows for the development of the towering thunderstorms that are the fundamental building blocks of a cyclone. Third, you need high humidity through a deep layer of the atmosphere. It's not enough to just have moist air at the surface. You need that moisture to extend thousands of feet up. This moisture is crucial because when it rises and cools, it condenses into cloud droplets and releases something called latent heat. This release of latent heat is the primary energy source that powers the storm. It warms the air, making it lighter, causing it to rise even faster, which pulls in more moist air from the surface, creating a powerful, self-sustaining feedback loop. The fourth ingredient is the Coriolis effect. The rotation of the Earth itself imparts a spin to the atmosphere. This force is what gives a cyclone its characteristic rotation, counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. This is also why cyclones almost never form within about 5 degrees of the equator. The Coriolis effect is weakest at the equator and gets stronger as you move toward the poles. Without enough of this spin-inducing force, a developing storm can't organize its circulation and will just fall apart. Fifth, you need a pre-existing disturbance. Cyclones don't just appear out of thin air in the middle of a calm ocean. They need a seed to grow from. This is usually a pre-existing low-level weather disturbance, like a tropical wave moving off the coast of Africa, a trough of low pressure, or even just a disorganized cluster of thunderstorms. This disturbance provides the initial focus point for the warm, moist air to converge and begin its journey skyward. And finally, the sixth ingredient is low vertical wind shear. Vertical wind shear is the change in wind speed and direction as you go higher up in the atmosphere. For a cyclone to form, this shear must be very low. Imagine trying to build a tall, straight tower of blocks. If the wind is blowing harder at the top than at the bottom, your tower will get tilted and fall over. It's the same with a cyclone. High wind shear tilts the storm's vertical structure, disrupting the flow of heat and moisture and effectively tearing the developing engine apart before it can get organized. So when all 6 of these ingredients come together, the stage is set for a cyclone to be born. The journey from a gentle disturbance to a monstrous major storm is a fascinating and often rapid process, marked by 4 distinct stages. It begins with what's called a tropical disturbance. This is really just a loose cluster of thunderstorms with a very slight atmospheric circulation. At this point, many of these disturbances just fizzle out and disappear without ever developing further. But if conditions remain favorable, the disturbance can become more organized. As the pressure in the center of the storm starts to drop, winds begin to circulate more strongly around that central point. When sustained wind speeds reach at least 23 miles per hour, the disturbance is upgraded to a tropical depression. A key feature here is that you can now draw at least one closed isobar, a line of equal pressure, around the storm center on a weather map. As the storm continues to intensify, drawing more and more energy from the warm ocean, its wind speeds increase. Once sustained winds reach 39 miles per hour, the depression is upgraded again, this time to a tropical storm. This is the point where it's given a name. The storm becomes much more organized, with a clear circular shape and developing spiral rain bands. It's now considered a self-sustaining system, a true heat engine that can continue to strengthen on its own. The final stage is reached when sustained wind speeds exceed 74 miles per hour. The storm officially becomes a hurricane, a typhoon, or a cyclone, depending on where it is in the world. A powerful rotation develops around a central core, and the storm's structure becomes highly organized. This is when the iconic eye of the storm often begins to form, that calm, often clear area right at the center. Surrounding the eye is the eye wall, a terrifying ring of intense thunderstorms where you find the strongest winds and the heaviest rainfall. This is the most destructive part of the storm. The process of a storm becoming a major one, like a Category 3, 4, or 5, is all about this structure becoming more efficient. As the central pressure plummets, the pressure difference between the calm eye and the violent eye wall becomes extreme, causing the winds to accelerate violently. All that latent heat being released in the eye wall fuels this intensification, turning the storm into a powerful and terrifying engine of destruction. These storms are born in 7 distinct ocean basins around the world. In the North Atlantic, the Caribbean, and the Gulf of Mexico, they're called hurricanes. The Northeast Pacific is actually the second most active basin, and they're also called hurricanes there. The most active basin on Earth, accounting for 1/3 of all activity, is the Northwest Pacific, where the storms are called typhoons. In the Indian Ocean and around Australia, they are called cyclones. The paths these storms take are generally guided westward by the trade winds near the equator. As they move toward the poles, they often get caught up in the westerly winds of the mid-latitudes, which can cause them to recurve and track eastward. Large high-pressure systems, like the Bermuda High in the Atlantic, act as steering wheels, dictating where these storms will go. Just as there are ingredients for a storm's birth, there are also storm killers. We mentioned high vertical wind shear, which tears a storm apart. Another is dry air. If dry air gets sucked into the storm circulation, it suppresses the thunderstorms and weakens the latent heat engine. Moving over cooler ocean waters will also rob the storm of its fuel, causing it to weaken. And of course, the biggest storm killer is landfall. When a cyclone moves over land, it's completely cut off from the warm, moist ocean air that fuels it. The increased friction over the land surface also helps to disrupt the storm's circulation, and they typically weaken and dissipate very rapidly. Predicting the path and intensity of these storms is one of the most critical jobs in meteorology. Forecasters use an arsenal of sophisticated technology. Geostationary satellites are the workhorses, providing continuous, real-time imagery from space. Then there's aircraft reconnaissance, the famous hurricane hunters. These brave crews fly specially equipped airplanes directly into the storms. They drop instruments called dropsondes, which fall through the storm and transmit back vital data on temperature, humidity, pressure, and wind speed at all levels. This gives us a detailed, three-dimensional picture of the storm structure. As a storm nears land, coastal Doppler radar provides a close-up look at its rainfall and wind fields. All of this data is then fed into a wide array of complex computer models. You may have heard of these models or seen their visualizations often called spaghetti plots, which show the predicted tracks from various models. These models are constantly improving, and they are the main reason why track forecasting has become so much more accurate in recent decades. The science of cyclone genesis is not static, because our planet's climate is changing, and this is having a profound impact on these storms. There is a strong consensus that while the total number of storms may not be increasing, the ones that do form are becoming more intense. Warmer oceans provide more fuel, which is leading to a higher proportion of major Category 4 and 5 storms. A warmer atmosphere can also hold more moisture, which means cyclones are producing much more rainfall, increasing the risk of devastating inland flooding far from the coast. On top of that, global sea level rise means that the storm surge pushed ashore by a cyclone is now starting from a higher baseline, allowing it to penetrate further inland and cause more damage. There's also evidence that climate change is contributing to more frequent instances of rapid intensification, where a storm's wind speeds increase dramatically in a short period of time. This makes forecasting their ultimate strength much more difficult and gives coastal communities less time to prepare. History has shown us the devastating power of these storms. The 1970 Great Bola Cyclone in Bangladesh created a massive storm surge that killed an estimated 500,000 people, making it the deadliest tropical cyclone in recorded history. In 2005, Hurricane Katrina's storm surge breached the levees in New Orleans, leading to catastrophic flooding and over $125 billion in damage. We've seen records for size with Typhoon Tip in 1979, which grew to an incredible 380 miles in diameter. We've seen records for wind speed with Hurricane Patricia in 2015, which had sustained winds of 215 miles per hour. And we've seen records for rainfall with Hurricane Harvey in 2017, which stalled over Texas and dropped over 60 inches of rain, causing historic flooding. The science of how a cyclone is born is a testament to the immense power of our planet's climate system. From the intricate dance of ingredients in the atmosphere and ocean, to the cutting-edge technology we use to track them, understanding these storms is a field of constant discovery. As our world continues to warm, this science will be more critical than ever, helping us to forecast, prepare, and protect vulnerable communities from the fury of these magnificent and terrifying natural giants.